So here's how it doesn't meet reality. So what it does is that it shows the nucleus, which it should, okay? And then you have like this S sublevel. So if there's one unit that's absolutely critical in terms of vocabulary, it's this unit, okay? You have to be able to differentiate between energy levels, sublevels, and orbitals, okay? When I talk about those three things, you have to know what I'm talking about. So if you go back to like Electron Hotel, what you'll notice is that those are like floors on the hotel. Some people like to think of energy levels as being like layers of an onion, okay? So if here's this nucleus, then this is going to be this first energy level. That's like the first layer of the onion, and that's the one that's going to be closest to the nucleus. So in the first energy level, and that only composed of hydrogen and helium. Okay, so one of the things that you've got to be able to do is use your periodic table. Okay, this is vital that you be able to use this periodic table. This seems horribly complicated, but it's really not if you can figure out like the secret code. So over here on hydrogen and helium, okay, those are the first two elements. And notice that they're the only ones up there on that first row. The reason that there's only two elements in that first row is because of the fact that in that first energy level, there is only one sublevel, and that is the S sublevel. And in the S sublevel, there's one orbital, and in each orbital is capable of holding 2 electrons, okay? So that's the nice thing. So if you slide back and go, oh, hydrogen, oh, here's the nucleus, oh, boom, 1 electron. Slide it over a little bit more, oh, boom, there's helium, there's 2, okay? So that's why there's only 2 elements across the top row of the periodic table, because the first energy level only has 1 sublevel, and it only holds 2 electrons. Now, here is where and it's cool, okay? You can see it, you can visualize it, you can spin it around, and it looks cool, okay? It looks cool. But here's the downside to this model. And in reality, these make these electrons look like they're stationary, okay? In reality, these electrons are moving close to the speed of light, okay? And they're not only are they spinning, okay, moving around the nucleus, they're actually spinning on their axis, kind of like I take this apple and I make it spin like this, okay? Now, some electrons spin in one direction, some electrons spin in the opposite direction. Now, when we talk about that, we really don't know what electrons are doing, okay? We can't see an individual electron. So what we call spin is that because we made some observations when electrons emit light. And the only way that we could really explain how this light looks differently, which we'll get into later, is the fact that one spins in one direction and one spins in the opposite direction. So don't get this visual like electrons are, like little basketballs, that you're spinning on your finger like this. Okay, you can visualize it that way, but we really don't know what electrons are doing. So the downside of this is that it makes them look stationary. In reality, they're moving very, very rapidly, and in reality, we don't know where the electrons are. All we can say is with a very high degree of probability where they are. Now, each sublevel has its own shape. So S is easy to remember, because all S sublevels are spherical. Okay, so in reality, what they're painting and they're showing on that model as like these 2 little dots, in reality, imagine that's like a 3-dimensional area, okay? And technically it's what we call an electron cloud. So within this S sublevel, in the first energy level, because there's only one orbital, it can hold at most 2 electrons. Now, as soon as you go past that, oh, now let's go to lithium. Oh, okay, now we're on to lithium. So lithium starts this second energy level, okay? So again, I don't care how you do this, if you like the periodic table with the S, P, and you like that, hey, that's cool, right? If you want to be able to use the periodic table, which is the preferred way to do this, that's cool. So you come down here, you start lithium. So the whole key to this is that it literally, if you can count, which you all can, you can figure out how to write orbital notations. Okay, literally, it is just counting. That's all. Okay? So if you go to here, come on. If you go to here, so this is what we call the S block. And we call it the S block because the S sublevel has one orbital and it holds 2 electrons. So anything here is going to fill, this first column is going to fill S1. Guess what? The second column is going to fill S2. So let's say you're down here, I gave you potassium. Oh, okay, right, potassium. That 4 indicates, oh, that's my highest occupied energy level. So I know potassium, its outer shell electrons are going to be 4s1. If I go down to rubidium, oh, rubidium is going to be 5s1. There you go. That's all you have to realize. Now, you go over here to like strontium. Oh, strontium, right. Strontium is going to be, you go across, oh, that's going to be 5s2. So if you use the periodic table, that allows you to figure all this stuff out. Now, over here, and again, if you can count, you've got this figured out. If you come over here to this big side over here, there's 1, 2, 3, 4, 5, 6. The reason that there are 6 columns there is because in the P sublevel, and this is a little bit more complicated than the S. So stay with me as I draw this. So imagine that you have an X, Y, and a Z axis. So imagine I'm like this. Here's my X, here's my Y. Let's screw that up. There's my Y. Erase. So here's my X, here's my Y, here's my Z. So imagine that you have a nucleus. Okay, that's going to be right there in the middle. That's where all the mass is located, right there. So then you have 1s, and that's spherical. Okay, so I've got this layer of this onion like this. Now again, visualize this is not in a plane like that is. Okay, it's in a sphere. So we filled up 1s. We put 2 electrons there. We don't know where they are. They're moving very quickly. They're occupying all this space. Then we're going to go to 2s. Okay, so 2s is going to hold 2 more electrons. Okay, and that's also 1 orbital. So all s orbitals, no matter where they are, only hold at most 2 electrons. Okay, now at this point, Mother Nature goes, I need to put more electrons in here. S sublevel is full. I'll go to the P sublevel. Now, the P sublevel is more complicated. Okay, so the P sublevel is like pear-shaped. That's how you remember it. So the P sublevel is pear-shaped. So what that means is that that's coming out here like this. So imagine these are balloons. So imagine these are like balloons like this, okay? So you'd have, now, these 2 balloons together make up the orbital. Don't think this is one orbital and that's another one, okay? So these 2 together are like this, okay? There's my X. You'd have another set like this, and then imagine that I've got another set coming out here like this, okay? So I've got 1 along the X, 1 along the Y, 1 along the Z. Got the visual. Now, why do you think that Mother Nature separates these as far away as they possibly can? Why do you think Mother Nature says, I'm going to put electrons in here, but I'm going to keep them as far away as I can?
Have the same charge.
Huh?
They have the same charge.
Yeah, they don't like each other. These electrons don't want to hang out, okay? You try and put these electrons together, electrons are going to go, screw you, okay? I don't like you, get away from me, okay? Yeah, we're going to hang out because we're attracted to the nucleus and we're trapped in a wave function, which we'll talk about later, but we really don't like each other. So Mother Nature goes, how can I put electrons in there, but yet maximize the distance away from them? So this together, this whole thing right here, makes up one p orbital. So we call this like the px, we call this the py, and we call this the pz. So that's why we know that there's three orbitals, because that maximizes the distance between them. So whenever electrons are being put around a nucleus, there's two competing forces. You have the repulsion between the two electrons, because they don't like each other, because they have the same charge, so the electrons don't want to be near each other. But that's balanced by the attraction towards the nucleus, because those are oppositely charged. So imagine this. So you got these chihuahuas that are running around. Okay, the chihuahuas go, man, I don't like you, get away from me. So the chihuahuas by themselves don't want to be in this area. Okay, they want to run as far away from each other as they possibly can. But they're going, man, we really like the St. Bernards and the German Shepherds and the nucleus. Man, they're cool, right? So they're conflicted, because like, I don't like the other chihuahuas, but I really like the St. Bernards. So, okay, I guess we'll stay. Okay, so that's the balance that has to happen. So you have this repulsion and you have this attraction. Now, here's what I don't want you to think. Okay, here's what I don't want you to think. I want you to out of your minds right now. I don't want you to think that electrons travel in like figure-8 patterns like this. Okay, do not think that. Get that out of your minds right now. Okay, get that out of your minds right now. So when we talk about these p orbitals, and a lot of times we'll draw it as like a figure-8, you have to remember, listen to me, listen to me, listen to me. Orbitals do not describe the path of the electrons. What they are regions of probability. Okay, that's all we're saying. So what we're saying is that these electrons are most likely to be found in these nodes. Okay, along the X, the Y, and the Z. Okay, and don't think that they're trapped in here and they're going, oh, it's like this inner, jail cell, and this is where the electrons, like the electrons are trapped inside the balloon, and that's the only place they can be. We don't know where the electrons are for certain. What we do know is with a high degree of probability, at any given point, this is where they're most likely going to be. Okay, that's all we can say. She's like, I don't know for certain where Luke is going to be at 8 o'clock on a Monday morning. I can say with a high degree of probability he's going to be in that chair. Okay, he might be in the back of the room. Okay, he might be in the lab next door. He might be at Starbucks. He might be in Paris, France. He might be on the moon. Small probability, but there's a chance. Okay, but most likely that's where he's going to be. Now, we'll get more into this later, but here's the odd thing. Once you try and observe where an electron is, you have to give it so much energy that you knock it out anyway, and we really don't know where it is. So, when we talk about orbitals, we're talking about probability. Okay, we don't know for certain where they are. Now, so here's what happens. So this is this 2p. Okay, so imagine you've got the first layer of your onion, 1s. Then you got the second layer of the onion, 2s. Okay, at that point, if you fill that, now you're up to 4 electrons. Now, once you go to 2p, then you're getting regions of probability like this. It's a little bit more complex. Okay. Now, after you fill 2p, what do you start to fill next? What do you fill after 2p? 3s. 3s. Now, so imagine 3s is out here. Now we got a third energy level. So now we have the third layer of the onion. Okay? 3s. Cool. Got it. All right. Then you're going to go to 3p. So now imagine with 3p, now you've got a third set of balloons farther out. Okay? Okay, great. We've got another region out here. Now, after you fill 3p, So now we filled 3s, and we filled 3p. Now what do you fill after 3p? This is where this big transition happens. If you're not sure, drag that little icon along the bottom.
3D.
What do you fill?
3D.
3D. Are you sure? After you fill, hold on. So we filled 1s, right? 1s2. Then we go 2s2. We go 2p6, right? What fills after 2p6? 3s2, right? Now, chutes and ladders. After you fill 3s, then what do you fill? 3p. Then what do you fill? Do you go from 3p to 3d, or do you go from 3p to 4s? 4s. Now, this is why, listen to me very, very carefully. This is why there's this huge gap right here. This is why you don't fill with scandium, titanium going across like this. This is why you don't have this block until you fill 4s. So this is why there's 4s, potassium, calcium, then you start going across, okay? So this is why there's this big gap here. This is why we don't fill the D block until we fill 4s. Now, the reason Mother Nature does that, the reason why you fill 4s and then you fill 3d, because Mother Nature is a lazy prima donna. Okay, Mother Nature is only going to do what's easiest for Mother Nature to do. Now, if you think the P sublevels are complicated, the D sublevels are even worse. So the D sublevels, now, listen to me very carefully. How many orbitals are in a D sublevel? 5. Okay? Now, if you're not sure, okay, oh, I think there's 5. Each orbital holds 2. That would mean there's 10. If you're on the test and you don't remember, like, God, I've completely spaced this off. I don't remember. Find the middle block. Count across. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's 10 columns across here. That means that it holds 10 electrons. Oh, right, 10 electrons. Cool. Each orbital holds 2. Divide that out. Divide 10 by 2, you get 5. So if you're on the test, okay, and your midterm, don't forget it's going to be on Friday. So, and you're on this and you flip out and go, man, it's a multiple choice question. How many sublevels are in it, or how many orbitals are in a D sublevel? It's like, oh, man, count, okay? P sublevel, count across there, there's 6. Now, in the F sublevel, how many can you hold? How many orbitals are in an F sublevel?
7.
7. That holds 14. Count across down here. Guess what? There's 14. Okay? So literally, you don't have to memorize anything. If you can count, you can do sublevels. Okay? They're really not that complicated. They look complicated, but if you figure out the pattern, they're really not. So the D sublevels get really weird. So the D sublevels actually exist in between the P sublevels, okay, and there's 5 of them. So these exist in this intermediate range in between them, okay, which are even more complicated. So Mother Nature goes, wow, it's much simpler to put 2 electrons out there in that 4th energy level than it is to start to fill the 3D. Okay, so Mother Nature sits there and goes, yeah, I don't want to put anything in those 3D. It's complicated, okay? So Mother Nature goes, I'll chuck those electrons out there in 4s. So, okay, cool, right? Then she's got 4s filled. It's like, okay, I'll start to fill 3D. So that's why Mother Nature fills 4s before she fills 3D, because Mother Nature is a lazy prima donna. So you keep this in mind when we begin to look at light. Mother Nature is a lazy prima donna. Mother Nature only does what's easiest for Mother Nature to do. Okay, so now Mother Nature has filled up 3D. It's like, okay, now I'll start to fill 4P. Okay, then she starts to fill 4P. Then she goes 5S. Okay, cool, now we'll fill up 5S, okay? So that's your sequence. So Mother Nature fills it in that sequence because Mother Nature's lazy. Now, the F sublevels are even weirder, okay? The F sublevels are actually donut-shaped probabilities that wrap around the lobes of the d orbitals, okay? So those are actually donut-shaped probabilities, okay? So then it's like, oh, that gets even weirder. So everybody has, that's what I don't like about this model. It's great because it shows you what's happening, but in reality, it just gets weird because to try and show you F sublevels, you've got little circle donut shapes and things like that. And again, here's the biggest misconception that I want you to get out of your minds right now. When we talk about the shapes of these orbitals, okay, we talk about the shapes of the orbitals, all they are of regions of probability, okay? That's all we can say, is that with a high degree of probability, this is where they are. And Mother Nature fills the lowest energy levels first before she transitions and moves to the highest energy levels. Okay, now, let's talk about the D sublevels. So, if you go across, you've got, let's start with like potassium. Okay, potassium, 4s1, and then you've got calcium, 4s2, and then you've got scandium, okay, which is 4s2, and then you start to fill 3d1. And then you've got titanium, 4s2, 3d2, and then you've got vanadium, 4s2, 3d3, and then you got chromium, 4s2. Okay. Now, somebody on your slider who's got pretty fine motor controls, slide across and tell me what the computer says the arrangement for chromium is.
The whole thing?
No, just like the last, like the 4s and the 3d.
The 4s, 3d, 5, 4s1?
Yep. Okay, now here's the deal. Chromium kind of breaks the pattern. Chromium is actually 4s1, 3d5. Now, why do you think Mother Nature goes 4s1, 3d5 as opposed to 4s2, 3d4? What is Mother Nature first and foremost? How would you describe Mother Nature?
Lazy.
Lazy prima donna. So why do you think it goes 4s1 and 3d5?
Because it's easier?
Because it's easier. It's less energy. Okay? So Mother Nature goes, hey, instead of putting 2 electrons out there in 4s and 4 electrons in 3d, what Mother Nature does is that she shifts one of those electrons back down and says, okay, I'm going to be equitable at this point. I'm going to put 5 electrons in 3d. This is going to be all about equity. So we're going to put 5 electrons in 3d, and I only have 1 electron in 4s. So chromium breaks the pattern, okay? So when you're going along, 4s2, you would think you would go 4s2, 3d4. In reality, it's 4s1, 3d5. Now, go across and find copper, Miles. Give me that same thing for copper.
3d10, 4s1.
Okay? Copper's the other one that breaks the pattern. Okay? So it's the 2 C's. It's chromium and copper. Those are the ones, when you're filling the sublevels, break the pattern. Because again, Mother Nature's a lazy prima donna. So Mother Nature sits there and goes, wow, this is going to be easier to put 1 electron up there in 3D and then go ahead and fill up the D sublevels and put 10 electrons in this. Now, when you go to the next one, which is zinc, zinc then completes the pattern, and zinc goes to 4s2, 3d10. So those are the 2 anomalies, okay, that break the pattern in filling these. Just remember the C's, chromium, copper, okay? When you're filling them, those break the pattern. Everything else follows exactly like you would expect. Got that? Kind of a cool visual so you can understand that. Okay. So here's what you've got. So when you do, like for example, these questions on 13, okay? I guarantee you, it's gonna be on the multiple choice portion of this test, it's gonna be on Friday, okay? These are your absolute home run questions that you have to know without fail. If you're a visual kind of person, get a 3x5 index card and write, okay, if this is how you learn, you can come in here and write, okay, on one side write the S sublevel. On the other side of that card write, oh, that holds 1 orbital and 2 electrons. Make one for P sublevel. Oh, that's 3 orbitals, holds at most 6 electrons. So if you're a flashcard kind of person, okay, and you like that, hey, cool, do that, right? Do that for the D, do that for the F. I promise you, those are the kind of things that you have to know without hesitation, okay, because it forms the whole basis of the periodic table. Now, if you're not a flashcard kind of person, use the periodic table. Oh, S sublevel. Oh, that holds 2. That's cool. D sublevel. Count across. There's 10. Oh, P sublevel. Count across. There's 6 columns. F sublevel. Count across. There's 14. Okay. How you figure this out makes no difference to me. But this is the absolute one of the backbone things that you have to know coming out of Chem 1. Is this idea of energy levels, sublevels, and orbitals. Okay. Keep those absolute, I cannot emphasize this, that and the mole. Going out of Chem 1, this first half of Chem 1 up to this first 9 weeks, those are the 2 probably most important things that you have to know. Concept of the mole, these electron configurations. Got that? Okay. Now, when you get into, like on page 13 in that packet, okay? Those are all, when you get down to like question number 10. So this, question 10 is a little tricky. It says, how many electrons can fit into a d orbital, a p orbital, or any kind of orbital? So what's your answer to number 10? 2. Okay? 2. It does not make, listen, it does not make any difference if it's a d orbital and p orbital or anything like that. Okay? Any orbital, no matter where it is, only holds 2 electrons. Now, this is where the confusion happens. So a d orbital, or an s or a p, whatever, only holds 2 electrons. That's it. Now, where the confusion happens if I said, and here's the difference in these questions. Now, if I said, how many orbitals are there in a d sublevel? Okay? This is where you have to have the vocabulary down. Oh, d sublevel, how many orbitals? D sublevel holds 5. Okay? F holds 7. P holds 6. But each orbital, no matter where it is, holds at most 2 electrons. This is another way the questions get tricky. If I said 5s2, 1s2, okay? What's the only difference between those 2 sublevels? What is the only difference between those 2? Grace. Think of an onion.
How many rings out of this?
Yeah. Which one's farther from the nucleus, 5s or 1s? 5s. Okay, it's a bigger layer to the onion. Okay, even though it's a much bigger onion, okay, it still only holds 2 electrons. Okay, and that's the cool thing about it, is that it only holds 2 electrons. Now, here's where the story goes full circle. So if you look at the history of the periodic table and Mendeleev and how he did all that, when Mendeleev laid out the periodic table and they based it upon atomic number and chemical properties, the beauty of it is they didn't know anything about sublevels. They didn't know anything about electrons, they didn't know anything about protons, neutrons, nothing like that. All they did was arrange it based upon chemical properties and atomic number. After they figured out sublevels, after they figured out orbitals, then they go, oh, this is why it works. So they arranged it based upon how the chemicals reacted. Later on, they figured out and said, oh, that makes sense. Okay? Now, let's talk about, speaking of chemical properties. If you look at sodium, or lithium, sodium, potassium. What do lithium and sodium, potassium all have in common in terms of their number of outer shell electrons? Lithium, sodium, potassium. How many outer shell electrons do all of those have? Do not make this difficult. Miles.
How many electrons do they have?
No, just the outer shell, how many, in the highest occupied energy level. Like sodium is 1s2, 2s1. Sodium is 1s2, 2s2, 2p6, and then 3s1. Potassium is 4s1. So how many electrons in the highest occupied energy level are all of those?
1.
1. Okay? So every element coming down like this has 1 outer shell electron. Now, move over. Beryllium, calcium. Luke, next column over. How many valence electrons do you think those have? Do not make this difficult. So if the first column has 1 valence electron, the next column over, how many do you think it might have? 2. So the next column over, all of those have 2 valence electrons. Now, go over here to the next column, okay? All of these have 3, 4, 5, 6, 7, and then when you hit the noble gases, all of those have 8. So if you're trying to figure out how many valence electrons there are in something, go to the periodic table. Oh, this has 1. This has 2, 3, 4, 5, 6, 7, 8. So literally, if you can count, you know how many valence electrons there are. Okay? That's it. 1, 2, 3, 4. Then here you go. Oh, this has D1, D2, D3, D4, D5, D6, D7, D7, D8, all the way up to D10. There's actually 2 that have D10 and 2 that have D5. So if you can count and use the periodic table, that's all you have to be able to do. Got that? Okay. So when you get down to question number 12, okay, I want to make sure everybody's cool with question number 12 on page 13. It says, how many electrons can fit in each of the following energy levels? So the first, the second, third, the fourth. Raman, how many electrons can I fit in the first energy level?
1. What? 2.
Which answer is it?
2.
Okay. Why 2?
Because any orbital can hold 2 the most.
And then the S sublevel only has
2.
electrons because it only has blank orbitals.
1.
1. Okay. Now, in the second energy level, Keaton, in the second energy level, how many, listen to me very carefully, in the second energy level, how many sublevels are there? What'd you say? 2. S and P, right? So in the second energy level, there's 2 sublevels. Okay? Now, how many orbitals, okay, how many orbitals, Izzy, are there in the second energy level?
4.
4. So there's a total of 4 orbitals. So Peyton, since there's 4 orbitals, how many electrons can you put in the second energy level? Maximum number. Right? What's the maximum number of electrons I can put in any orbital? Huh?
I wasn't here for that lecture, I'm sorry.
Okay, my bad. Ella. What's the maximum number of electrons I can put in any orbital?
8, or in this one, 8. 2.
2. I have 4 orbitals.
Oh, so 8.
Yeah, 8. Total is 8, but each orbital can hold
2.
2. So, boom, there you go. 8, right? Yes?
What's the BOHR model?
The Bohr model?
Yeah.
We'll talk about that.
Did you figure out what it is?
Okay. Bohr model is basically where they're like electrons or like planets. Okay? That's
So
it.
it's like that.
Yeah.
Okay.
Now, in the third, Carter, how many different sublevels are in the third energy level?
3.
What are they?
S, P, and F.
SP and
D.
D. How many orbitals are in the S sublevel, Carter? How many orbitals are in the S sublevel?
1,
1. How about the P?
3,
How about the D?
5,
5. Add those all together, check my math, I get
9,
9 times 2 gets me
18.
18. Okay? Go with this, right? Now, fourth. How many sublevels are in the fourth energy level? Alec. How many sublevels are in the fourth energy level?
4,
4. And they are S,
P, D, and F.
D, and F. See the pattern? So, we just said that the SPD have 9. So the F sublevel has how many orbitals? Miles, how many orbitals are in the F sublevel?
7.
9 plus 7, check my math, gets me 16. 16 times 2 gets me 32. So those are your answers. That last one on 12. 2, 8, 18, 32. Okay? Promise you, that's something that you have to know without hesitation. Okay. Now, over on page 14. Okay? And this is so vital important when you look at how you fill these energy levels. So, in this question, as example number 2, you've got 4D. So you've got 1, 2, 3, 4, 5. Each dashed line represents an orbital. Okay? Now, here's the deal. Remember, you only talk about putting electrons in each orbital, and you put 1 in each orbital until they're full, then you start to double them up. The reason being is that electrons don't like each other, and Mother Nature goes, hey, I'm not going to make you guys hang out unless I have to, because I know you don't like each other. Mother Nature goes, y'all don't like each other. Mother Nature goes, I could care less. It's like imagine that you're a parent and you have twins and they don't like each other or they're fighting, okay? What do? You put them in separate rooms. You don't go, no, you two are fussing and fighting each other. I'm going to make you sit side by side, okay? Just so I can hear you two complain about how much you don't like each other. No. Mother Nature is like a parent. We're going to put you two as far away from each other as we possibly can because I don't want to hear you two fussing, okay? So that's basically what happens. So, how this is done, you have up arrows, which means that what we're meaning by an up arrow is that the electrons are spinning clockwise, okay? Down arrows just mean that they spin counterclockwise. So listen to me. Once you put 2 electrons in an orbital, the only difference is the way they spin, okay? One spins clockwise, the other one spins counterclockwise. We really don't know which one is which. We just know that this is something that we call spin. We call it clockwise, we call it counterclockwise. So when you get to question number 3 on page 14, it says, what does it mean to have the arrow pointing down? All that means is that we're saying that electron is spinning counterclockwise. Okay? That's all that means. If it was pointing up, we would say it was spinning clockwise. Okay? Don't make this difficult. So when you get to question number 6, so a lot of times questions are asked not so much but what is right, but what is wrong. So when you get down there to question number 6, it has 2D, and then it has 5 spaces after it. Okay?
No, it has 4 spaces.
Oh, 4 spaces, my bad. 4. So there's 2 things that's wrong. Number 1, D sublevels have how many orbitals?
5.
5. So number 1, it doesn't have enough orbitals. It only has 4. It should have 5. Can the second energy level have a D sublevel?
No.
No, because what's the first energy level that has a D sublevel?
3.
3. Okay? So that's what's wrong with it. There's 2 things. The second energy level only has an S and a P, and even if it did have one, it would have to have 5 orbitals. Okay? Got that. So that should allow you to figure out, then on number 7, it says, on that one, your 4th energy level, F sublevel spinning clockwise. Go out there, write out 4F, put 7 dashes. Do you want to point that arrow up, or do you want to point that arrow down?
Up.
Up. There you go. So put one arrow pointing up. That's all you have to do. So that should allow you to, then you got some questions to answer on that middle of page 15. So you shouldn't have any trouble with that. And then at that point, you should be able to get all the way through page 17. Now, let's talk about what I want on 17, where it has that Bohr model. Okay? And what I want on these. So on lithium, so this is what I'm looking for. Here's your chart. Element, and they want the isotope symbol. The Bohr model, orbital diagram, electron configuration. Okay, so when you look at lithium, let's start with the relative atomic mass. Luke, what's the relative atomic mass of lithium on your periodic table?
6.941.
Okay, so let's just round that up to 7. Remember that each proton and each neutron has a relative atomic mass of 1. So on average, and remember, this is an average. What you're seeing is an average. So what you're saying is that on average, most lithium atoms are going to have a mass number of 7. Okay? So we got lithium, right? How many protons are in each lithium atom? 3. So we got that. That's all you have to have for that part. Okay? 7, 3, lithium, boom, there you go. So on the Bohr model, come in here and put a small dot, put 1 layer of an onion, and put 2 electrons on that, put another layer of the onion, and put an electron there. That's all you have to do. Okay? Not difficult. Then on the orbital diagram, write 1s, put a dash, put an up, put it down, and then go 2s, put an up. Okay? Always start with your ups first. Always, for whatever reason, somebody decided, oh, we're optimistic people, we'll put the up arrows first. And then on your electron configuration, just write 1s2, 2s1. Okay? So you're going to do that for sodium, calcium. So right now, Miles, stop that. So I'll give you little. Now, Here's one of the most important things in terms of understanding how atoms are going to bond together. So might be asked like, how many single electrons are in a carbon atom? Okay? Now, the only way you can answer a question like this is to write out the orbital diagram. Okay, that's it. That is the only way. So you're going to sit there and go, okay, 1s2, okay, or 1s, and then put your,
But Mr. Bridgestone,
what?
can't you know because there's like an odd number of things next to the electron configuration? You know what I'm saying?
Hold on. Yes and no.
You can know from that.
Hold on. Yeah. So then you got 2s, right? And there's 2 electrons there, up and a down. And then you've got 3s, right? So since it asks for how many single electrons there are, so carbon itself is 1s2, 2s2, 2p2, right? Okay? So here's the question. How many single electrons are in a carbon atom? Don't put both electrons here, okay? Because they don't like each other. You got to put one in each of these orbitals. So you got one like this, one like this. So this answer for carbon, even though it has 6 overall valence electrons, 6 overall electrons, and it has what we call 4 valence electrons. The valence electrons are in the highest occupied energy level. So carbon has 6 total electrons. It has 4 valence electrons in that second energy level. But it has 2 single unbound pairs of electrons. Okay, and the only way you can figure that out is to write that out. Now, if you go to nitrogen, okay, nitrogen is very similar. 1s2, 2s2, 2p, that's actually 2p. And then you got 2p3. So, nitrogen has 3, yes.
But we can know that without writing it out.
Hold on, just hold on, just chill out, okay? Just chill out. So yes, if you count across those first columns, you go boron, nitrogen, oxygen, whatever, okay? That's going to have 3 unbound pairs of electrons. But then, after nitrogen, what do you have? What's the next element after nitrogen? Oxygen, right? Hopefully. So oxygen is 1s2, 2s2, 2p4. So then, because there's 4, you go up, you go up, you go up, you go down. So here's the deal. Oxygen and carbon, even though they have completely different numbers of electrons, both have 2 unbound pairs of electrons. Okay? Now, what you'll see later on is that oxygen, because it's only missing 2 electrons, will gain 2 electrons to fill up those orbitals. Carbon, because it has 4 valence electrons, it's just going to share those. So that's the beauty of, if you write it out, filling up the orbital notation. Even though carbon and oxygen both have 2 unbound pairs of electrons, how they behave in terms of taking in electrons is vastly different. Carbon's going to share electrons. Oxygen is actually going to gain electrons to form ions. That's the advantage of writing out that orbital notation, because it allows you to see exactly which orbital is going to be filled. So it just gives you some more information. You're right, you can, but this allows you to see more in terms of what's going to happen when oxygen reacts versus how carbon reacts. That's the advantage of it. Okay? All right, we're cool? Got it?
No.
Get there. That's all I'm telling you, get there. So, there is going to be so much of this on that test on Friday, I'm telling you. Okay, so we have one last big topic, and that's light and sound. So, and you're thinking, what does light have to do with this? Okay? So, basically, if we can't directly observe what's happening inside an atom, okay, we can't. We don't know. We can talk about a mathematical model, and it's worked beautifully, it's very predictive in nature, and it's wonderful, okay? But to have this idea that we can actually watch an electron move, like we can watch the moon, okay? Can't do it. Cannot do it. Cannot. Okay, electrons are too small, they move too fast. Cannot make that observation. So what we do is we observe the light that's given off. Now, when you talk about any form of a wave, basically you talk about two things. When you talk about waves, you talk about wavelength and that's typically measured in meters. And you talk about frequency, which is typically measured in hertz or Hz or 1/seconds or s to the minus 1. Okay? So let me kind of give you some examples of frequency and things like that. So what I have here is two different tuning forks, okay? And they're stamped with different frequencies, okay? So this one vibrates at 880 hertz. What that means is that vibrates 880 times per second. This is 883. So this vibrates a little bit more times per second than the 880 does. So when you see hertz, that's how many vibrations per second that occur. So if I hit this one, okay, that has a certain sound. So what's happening for you to hear this is that as that tuning fork goes back and forth, it creates a disturbance. And what it does is that it sends that disturbance through the air. That disturbance hits your eardrum. Your eardrum vibrates. It sends that signal through your eardrum to the bones of your inner ear. That gets connected to your auditory nerve. Your auditory nerves sends that to your brain, and your brain says, wow, Burkamp's making something vibrate. Okay? Now, if I do 883, okay, that's a little bit different pitch, but not much. But what I want you to get out of these demonstrations that I'm going to do is that things vibrate differently depending upon the system. So this vibrates at 880 hertz. This vibrates at 883 hertz. Now, what I've got here is called an Ames tube. Okay, it's open on both ends. Okay, there's nothing magic about it. Okay, so if I take the 883 hertz, okay, and hold that up, okay, nothing really happens. But if I take the 880 hertz, now the cool thing is, even if I take that away, the air inside is still vibrating at that frequency. Okay? So what this means is that systems, if struck with just the right frequency, vibrate at a natural frequency. It's called a resonance frequency. So if I take the 880 and hold this up, so what's happening is that that air inside of there, because it hit that resonant frequency, is continuing to vibrate. So that air inside is still going back and forth, back and forth, back and forth. But the 883, when I do this, won't do it, because this doesn't match the resonant frequency of the tube. the 880 does. So what I want you to, here I'm just trying to lay the groundwork, is that things in nature will vibrate with a natural resonance. So what I've got here is a wine glass. Okay? Not a big deal. Now, this is just vinegar. I just do this so I get the oils off my finger. Okay? So this is vibrating with a certain natural frequency. Now, if I add water to it, now when I do that, so I've changed the conditions of the system. And since I changed the conditions of the system, I changed that natural resonant frequency. So here's the deal. So if I add more and more water to it, what happens to the pitch? Does the pitch go up or does the pitch go down?
Down.
Pitch goes down. So this one, there's an inverse relationship between the amount of mass in the system and the frequency. So as I put more and more mass in the system, the frequency goes lower. So if I take this and pour this out, okay, and get rid of a lot of it, now what should happen?
Pitch will go up.
Yeah, so now, that's going to vibrate with very high pitch because I've dropped the mass. So, here's what I want you to get for now. Natural systems vibrate with a certain frequency based upon the system. Okay, got that? All right, Miles, I need you to disconnect that camera, and we're going to go to the back of the room. When you talk about waves, talk about, I'm too old to be on like that. Yeah, kind of yoga. I might need some help getting up. What? I'm going to try not to. Okay, so what I can do is I can make this vibrate like this. Now, what's happening here, let me tighten this up a little bit. I'm going to change the system a little bit. So, right here, I'm making this thing vibrate with a certain wavelength. Now, I want you to visualize that we could stop this. So as that was going, what that was representing was an entire wavelength. So one end started at Ella, and then, okay, so this is what we got going. So this is one complete wavelength. So Ella's end isn't moving, my end isn't moving, and there's a point in the middle that's pretty stationary as well. So when you talk about a wavelength, it's starting at one point, it goes out, it goes through a middle, and then it goes back. So that's what we talk about when we're talking about wavelength. Now, when you're talking about frequency, frequency is how many waves go past a certain second. So, Raman, here's the deal. Okay? Right? You can handle this. What I want you to count is how many times a wave goes towards you. Okay? So like, when I get this going, okay, so that would be like 1, 2, 3, 4. Okay? Now, somebody get their phone, and we need to count out, and somebody time out 30 seconds. So get their phone and time out. You can do this. Okay? Grace, are you ready? Okay, so I'm going to tell you, you're going to time 30 seconds, and you're going to count. You ready, Raman?
Yeah, I'm sorry.
Grace, I'll tell you when to start. Okay? Okay, Grace, start your clock. Let me know when you get to 30 seconds, Grace.
Okay.
Okay, how many did you count?
34.
Okay, so what that means is that there's roughly about 1 wave per second. Okay, there's 30 seconds, it's about 34. Okay? Now, I'm going to change the system. Okay? Grace, we're going to do another 30 seconds. Okay? It's going to require more effort. Okay. Yes. Okay, well maybe I'll slow it down a little bit.
Yeah, slow down. My brain's not that fast. Thank you.
How about that one? Can you count that one?
Like, this one right here?
Yep.
Okay. Well, there's like 5 of them. So.
Just count, just pick one.
Okay.
Okay. Gracie, you ready?
Yep.
Okay, go.
Oh no, I lost my count.
Keep counting. Let me know when you get to 30, Grace. I'm getting tired.
Oh, she said 5.
Oh, how many did you get? Roughly. A lot more?
I counted to 88.
88.
75.
I got
74. Okay, here's the point. There was a lot more, right? Now here's what I want you to see.
There was no slower than 88.
What happened to the wavelength when I did this? Wavelength became shorter, right? Because this was like an entire wavelength, okay? This one, okay, right, is a lot shorter. So here's what I want you to get. As wavelength becomes shorter, what happens to the frequency? It increases. So is there a direct or indirect relationship between wavelength and frequency? Wavelength gets shorter, frequency gets higher, so there is an inverse relationship. Now, what I want you to watch is how much energy I have to put into the system. Okay? So when I'm like this, okay, that's a pretty long wavelength. Okay? And I'm pretty laid back. Okay? This isn't tough to do, right? Now, if I were to do something like this, okay? Now, what's happened to the frequency? It's gone up. What's happened to the wavelength? Down. But what's happened to the amount of energy that I have to put in to make it vibrate? Increases. So if I want a really, really short wavelength like this, okay, I have to work really hard. So what's the relationship between energy and frequency? Direct or inverse? Direct. Because as frequency goes up, energy goes up. But as frequency goes up, wavelength goes down. Got the visual?
Yes.
Okay, all right, let go.
Oh no, Mr. Kim, you gotta need help out.
I think you got it.
Oh no.
Is the Greek letter lambda. Okay? Kind of like a walking stick with a hook on the end of it. Okay? So that's the Greek letter lambda. For frequency, sometimes you see it written as the letter F. Okay? Sometimes you see it written as the Greek letter nu. Okay? Most of the time they've kind of shifted towards frequency because people got V confused with velocity. So what we're going to use is frequency. We're going to use the capital letter F. So here's the deal. So as you decrease the wavelength, what happens to the frequency? Rami, as I made that wavelength shorter and shorter and shorter, what happened to the frequency?
Wait, can you repeat that question?
As I made that wavelength, as I went from that wavelength being like this to that wavelength being like this. As I shortened the
Oh, the
wavelength,
frequency?
what happened to the frequency?
Up.
Frequency went up. Okay? So there's an inverse relationship between wavelength and frequency.
Frequency.
Now, but as I increased the frequency, what happened to the energy that it took to make it vibrate? It went up. That went higher. Okay? So as frequency goes up, energy goes up. Now, let's tie it all together. As I decrease the wavelength, what happens to the energy?
Up.
It goes up. Because as I shrink the wavelength, I make the frequency go up. Therefore, with a higher frequency, that requires more energy. Now, when you talk about light, okay, and this is, observing light is how we figure out the structure of atoms. So you have one big equation, and that's C equals lambda times frequency. And C is the speed of light, which is 3.00 times 10 to the 8th meters per second. Okay? Now, we talked about this. To give you an idea of just how fast that is, okay? If you could turn on a flashlight and make it go exactly around the Earth, it would take about that much time for that beam of light to travel all the way around the Earth. Okay? It isn't like part way around that. It's all the way around the Earth. Turn on that flashlight, you can snap your fingers, that beam of light has made it back to you. It's a really, 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 really big number. Now, this wavelength is going to be in meters. Okay? That's it. It's a distance. So when you're talking about wavelength, you're talking about the distance from like where it starts to when it gets back to that point. Some wavelengths are very, very long, like some radio waves might have 2 or 3 meters long. Some wavelengths for electromagnetic radiation, like X-rays, are very, 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 very short. So you have this whole gamut of potential wavelengths. Now, this is frequency, which is 1 over seconds. Now, this is where the magic happens. So if you look at the units, speed of light is in meters per second. That's a wavelength measured in meters multiplied by a frequency of 1 over seconds. Oh, meters times 1 over seconds, that's cool. We get meters per second. That's what the speed of light is measured in. Now, here's why what I just did works. The speed of light is a constant. Okay, you're not going to change that value. The speed of light is a fixed value, 3.00 times 10 to the 8th meters per second. Okay? So what this means is that when I multiply these two numbers together, I always have to get the same value. This is why there's an inverse relationship between wavelength and frequency. I always have to get 3.00 times 10 to the 8th meters per second. Okay? So as one number gets bigger, the other number has to get smaller. So here's how this plays out. So I would give you something like this. What is the frequency if the wavelength equals 5.0 times 10 to the negative 5th meters, which is pretty small, okay? That's very, 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 very much less than a meter. So here's the deal. If I've given you the wavelength, find the frequency. Oh, well, 3.00 times 10 to the 8th meters per second equals the wavelength, 5.0 times 10 to the negative 5th meters, times the frequency. So what are you going to do? Peyton, how am I going to get frequency by itself?
You gotta move the wavelength value.
Yeah, bingo. All I have to do is divide this by the wavelength. So divide this by 5.0 times 10 to the negative 5th. Now, meters. So look what happens. The meters cancel out. I get 1 over seconds. Boom. I'm done. That's it. That's all you have to do. Now, if I give you the frequency, multiply that by, if I give you the frequency and ask you to find the wavelength, divide that. Now, here's the other big equation. And that's E equals HF. Now, this is what's known as Planck's constant, 6.626 times 10 to the negative 34th. And it has units of joule seconds. We've talked about joules before. We talked about energy. Remember, energy is measured in joules? Okay? So this is the cool part about this. Look what happens to the units. So you have Planck's constant, which is in joule seconds. You have frequency, which is 1 over seconds. The seconds cancel out, you get joules. And that's what energy is made of. So what this gives you is the energy in a single photon of light. It might be a microwave, it might be a radio wave, it might be red light, it might be green light. Okay? This is the energy in a single photon. It's typically a very, very, very small number. Okay? Because you're talking about the energy in a single bundle of light. So, somebody take your calculator. Let's run through this right quick. So somebody take 3.00, and remember, hit that EE key. Do not type in times 10. If you like to store numbers, what I would do is I would store this 6.626 times 10 to the negative 34th, and I would store the speed of light, because you're going to be using those numbers a lot. So, somebody take 3.00 times 10 to the 8th, divide that by 5.0 times 10 to the negative 5th. What do you get? Give me that while I hand this out.
Thank you.
I forgot what the numbers were, Mr. Brickamp. Could you tell me them again? So I can type them
Oh,
in.
I get it. Frequency 451.
Okay, so somebody take the speed of light, 3.00 times 10 to the 8th meters per second, and divide that by 5.0 times 10 to the negative 5th. What do you get?
Why?
6 something. 6.0 times 10 to the what?
12.
Times 10 to the 12th hertz. So, Raman struggled to count 34. Okay, imagine trying to count 10 to the 12th vibrations per second. Okay, per second. What that means is that photons vibrate very, 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 very quickly. Now, if you want to find the energy, takes Planck's constant 6.626 times 10 to the negative 34th joule seconds, and then multiply that by 6.0 times 10 to the 12th hertz, which is 1 over seconds. The seconds cancel out. You get joules. So somebody takes 6.626 times 10 to the negative 34th times 6.0 times 10 to the 12th. You should get something times 10 to the negative 21st, something like that. Make sure, okay, the bell's gonna ring. Make sure to put those iPads back, plug those in. This assignment is due tomorrow.